When we talk about oscillators, one of the key ideas is called the period. So let's talk about what is the period. Let's imagine a block on a spring, which is one of our two kinds of oscillators. It starts in the middle and it goes to the left and then it goes to the right. It has this motion, the backwards and forwards oscillating motion. So we say it starts perhaps at the left side and travels right and left, and it's come back to the place where it started again. So the time it takes to do one circuit, one oscillation from the left to the right and back, that's one period. So if a block goes, that might be a fast period, and if it's traveling slowly, that's a slow period. When we talk about period, we use the letter capital T to talk about period. Because period is a time, it's measured with the units seconds, just like normal time. We distinguish between little t for regular time and capital T when we're talking specifically about something that is oscillating with a period. So capital T is the time of a period of an oscillator. It turns out that there's a formula for the period of both a spring and a pendulum. We're going to look at the formula for the period of a spring in this video. There it is. The period equals 2 pi big ol' square root m divided by k. So let's talk about what this means a little bit. So here's a block on a spring. And the block has a mass and the spring has that spring constant K. We're going to imagine that the block starts on the left side here and is oscillating to the right and to the left. So the period is the time it takes to start from here on the left side, travel to the right and travel all the way back. One oscillation. So we can calculate what the period of this spring system will be with this formula, T equals 2 pi square root m over k. Let's just do an example. Let's put in some ordinary numbers. So K is 300 newtons per meter with a block of mass 1.6 kilograms. Let's see what we get for the period. After the calculator, I get the period is 0.45 seconds. So again, the period is the time it takes to travel from the left to the right and back again, 0.45 seconds. Great. So that feels realistic. It's kind of fast, not so fast, but not so slow. And I want you to notice a couple of things about this formula. Firstly, the delta x, which is the amount it moves away from the center, that's not part of the period formula. So if I would take this same block and give it a little delta x, it would move slowly, but have the period of 0.45 seconds. And if I were to give it a large delta x, it would travel much faster, but have the same period. So it doesn't matter how far it's traveling. What does matter is the mass of the block and the strength of the spring. Basically, this formula is saying if a block is heavier, it will take longer to travel, but if a spring is stronger, it will make it go faster. And that kind of makes sense. AP Physics likes to ask questions about proportionality, especially with formulas like this that have square roots or squares in them. So let's do a question or two like that. Let's imagine there's a spring system and there's a block of mass m naught and spring constant k naught. We could say that the period is going to be this. Okay, not very helpful so far. Now we bring another block that has mass 2m. What's going to be the period of the new system? So there's a heavier block with the same spring. We'll call this period period 1, and now we're going to calculate period 2. So period 2 is going to be this, 2 pi square root 2m naught over k naught. So how much larger is this one than this one? It's square root 2 larger. I like to rearrange it this way. How can I make this one look exactly like this one, but a constant attached in front of it? So I just need to take out the square root 2 from that bit. So I just pop square root 2 out, and then I'm going to write this with brackets and put that at the very front. And this is identical to T1. So I could just rewrite this equation and put T1 in there, and I write like this. So the period 2 equals square root 2 times period 1. So the idea is if I double the mass, then I'm not going to double the period. I'm going to get square root 2 bigger period. These are not linearly proportional. These are square root proportional. Okay, that's the idea of the period of a spring system that's oscillating. We're also going to look at the period of a pendulum system that's oscillating.